We have one final piece in 9.5 that I figured was a good thing to do on just like a short day at home. And it's dealing with this one theorem that you see on the screen in front of you. We're going to talk about what it means to be absolutely convergent versus something called conditional convergence. And basically, you're going to read this theorem like a flow chart, where you're going to kind of go through, check number one, see if it works. If it doesn't, check number two. If it doesn't, check number three. So you're going to go in order. This is not a topic that shows up a ton on the AP test, but I have seen periodically them asking a question about this. So I want to make sure it's something that you don't miss because you're not familiar with the wording that they're going to use. So first, to be absolutely convergent, it actually means what it sounds like. It means that if you take the absolute value around the series, which would get rid of anything that's negative, if you can prove that that converges, then we would say it's absolutely convergent because it converges when you take an absolute value. The process to do this is to basically ignore anything that alternates, ignore anything that would create a negative, and then use one of the other tests. So don't use the alternating series test because we're going to ignore that, but see if it's a p-series or see if it's a geometric series or see if you can do a comparison. So use one of the other tests that we've gone through and learned. If that doesn't work, so if you take the absolute value and you are left with something that doesn't converge, maybe you find that it diverges with a different test, then you're going to go to option 2. Option 2 says that it will be conditionally convergent if you can show that the series converges even if the absolute value didn't. To do this step, if option 1 doesn't work, option 2, you're going to go to the AST, the alternating series test, meaning show that my terms are decreasing, show that the limit of it goes to 0, and since it alternates and the limit goes to 0, it will converge by the alternating series test. If neither of those things are true, then you're going to automatically drop down to the third option, which is that it diverges, and the proof for the diverges will always be because you did an nth term test. So those are your kind of your 3-step process. So I want to show you one of each, one that works for the first, one that doesn't work for the first but works for the second, and one that you have to go all the way to the third. So here's the first one. This one has a very funky alternating part, but when I take the absolute value of all of that, you are going to end up with just the series 1 over 3 to the n when I take the absolute value. All of this stuff up here is just going to create that negative sign. It may not alternate perfectly, but it will kind of have periodic negatives that we want to get rid of. When I look at this, I know that this is geometric. I know that my ratio is a third, which is less than 1. So I can say that this converges, and you'll actually hear the term converges absolutely because you did the absolute value around it. And the reasoning is you use the geometric test. That actually, if it works right away in the first one, will be the quickest problems you'll run into. So the second option in that kind of flow chart is you take the absolute value. You are left with something that you are left with 1 over the square root of n. This is a p-series. P is a half because it's being square rooted, and a half is less than 1, so this is a diverging p-series. So what that tells me is it is not an absolute converging, because when I took the absolute value, I was not left with something that converges. So my next step is to do an alternating series and say, well, I know it was alternating in the beginning. What if I try that test? So with the alternating series test, you want to check and make sure that when you take the limit of whatever is left without the alternating piece, so the 1 over square root of n, goes to 0. This definitely will go to 0 because you have a higher degree. You actually have the only degree in the bottom, so you get 0. So we say that this converges conditionally. And the reason they say conditionally, it's under the condition that you consider that it does alternate. And you're doing, you're doing the alternating series test, AST. Your third option, kind of the last default in that chart, is that you take the absolute value and you are left with n squared over n squared plus 1. I am not going to be able to come up with a test that tells me that converges. In fact, the first thing I notice is when I take the limit of that and I get 1, which is not 0, that tells me that it will diverge. It will always diverge. And the reason for the diverging with all of these will be because you did the nth term test for divergence. So that's kind of the process. Like if they ask for absolute versus conditional, absolute, you ignore anything that's negative, take the absolute value and see if you can use a p-series, a geometric series, a comparison series. If that doesn't work, then we're going to look at it and say, well, it was an alternating series. So can we say that it converges by the condition that it's alternating? And that would be the AST. And then our last kind of option there is that we get a limit that does not equal 0. So it would fail that AST. It will fail that alternating series test. So it diverges by nth term. I don't think you should expect to see a lot of questions on the AP test that asks about it. I've seen a few, but it is nice to know when they use words like absolute and conditional, that's what they're referring to. And there you have the end of 9.5.